Hello, class. Welcome to today's lesson. So I was planning to do this in the Meet, but the Meets are currently not working, as you know. So I'm going to record it and put it out as an Edpuzzle for you instead. So what we're going to do in today's lesson is a little bit of preparation for the next section. You guys are familiar with the reciprocal identities. Okay, we learned these in the past, and it was a way to relate the reciprocals, sine and cosecant, cosine and secant, and tangent and cotangent, and so on. And we use this when we put evaluated in the calculator or solve for theta when using a calculator. So the reciprocal identities, they're just relationships of equivalencies. So these are equivalent to each other, these are equivalent to each other, these are equivalent to each other. And sometimes we use them in our work, especially with calculator. There's another set of identities that you need to be aware of. They're called the quotient identities. You need to write this down. Okay. And what the quotient identities relate, they relate tangent with sine and cosine. And they relate cotangent with sine and cosine as well. Okay, so make sure you go ahead and write these down. So there's only two of them for our quotient identities, and its tangent is always going to be equal to sine over cosine, and cotangent will always be cosine over sine. So it's just another way to relate some of these trig functions. And what we can do actually is we can go ahead and prove pretty quickly that tangent is equal to sine over cosine. So go ahead and write this down. Let's start with sine over cosine. And by the way, when you see the word prove or you think proof, don't think of those two-column proofs from geometry. This is going to be quicker, shorter, just a little bit of algebra, okay? So let's prove that this is equal to tangent. We're going to start with sine over cosine. So if I start with sine, we know the definition of sine is opposite over hypotenuse because of SOHCAHTOA, right? So no matter what right triangle we're using, sine is going to be the opposite side compared to the hypotenuse. That's the definition. And no matter what right triangle we're using, if we have the same angle here, see how these match? Then cosine is going to be adjacent over hypotenuse. And what we have is a complex fraction. So we can think of this as opposite over hypotenuse divided by adjacent over hypotenuse. And in order to divide by a fraction, you guys like to same, change, flip. Okay, so we're going to keep the first fraction the same, change to multiplication, and flip the second fraction. What's going to happen here is hypotenuse over hypotenuse is going to reduce out. No matter what the length of the hypotenuse is, if those two match, it's going to reduce to 1, which leaves you with opposite over adjacent. And almost like a magic trick, what is opposite over adjacent? That's the definition of tangent. Ooh, I just fit it on the paper. So if you look, we started with sine over cosine, and we ended at tangent. These are equal to each other, all right? You could prove this one in a similar fashion. So if you liked that little bit of algebra we just did, feel free to do that, but you don't have to. And I just want to take you back and show you some examples from our past. Even though we did just prove this in general, that always works, I want to show you with some numbers, just as some examples. So you don't need to write down the next part. Okay. I found some notes from earlier in the year. I don't know, you probably won't remember, but this is from the very first time we did SOHCAHTOA. We were doing, we used a PowerPoint and we were doing SOHCAHTOA. And we can take a look at this and just see that indeed sine over cosine gives you tangent. So if you take a look at this example, you don't need to write this part. I just want to show you that if you have sine over cosine, you get the value of tangent. So sine for this example was 3/5. Cosine for this example was 4/5. And instead of dividing by 4/5, if I do same, change, flip, multiply by the reciprocal, the 5s reduce, just like the hypotenuse reduced before, and we get 3/4, and that's what tangent is. All right. So one thing you might be thinking is, okay, I see that it works, but why would we ever do that? In the next section, we will actually use the fact that tangent is sine over cosine. That'll actually be helpful. So right now, it's just kind of for your information, but in the next section, we'll actually use that information. And I just want to show you one more, because that example that I just quickly showed didn't have any radicals. I want to show you it works with radicals too. So here's another example. Oh, look, it's from November 9th is when we did this. Okay. So if you look at this example, we have our values for all 6 trig functions for this triangle. And I'm just going to use these numbers to show you that indeed sine over cosine is tangent. Or we could do cosine over sine and get cotangent. But the one that's going to be more useful for us, this is the one we're going to use more often. We don't use this one too often. Okay? So just to give you another example, you don't need to write this. If we have sine is 3/8 and cosine is that, tangent will be equal to sine over cosine. So if I start with sine, okay, and then I divide by cosine, I'm going to have 3/8 over radical 55 over 8. And when I divide, instead of dividing by a fraction, we multiplied by the reciprocal. The 8's reduce out here. We get 3 over radical 55. And you might look and say, oh, that doesn't match. But it does. That's what this was. And if we simplify this by rationalizing the denominator, by multiplying by radical 55 over radical 55, I did not mean to reduce that. What I meant to do, because that would take me right back to here. I have 3 radical 55, and when you multiply these together, you get 55. That's what tangent was. All right, so it works. It does work. Okay, so that's the first part of the work I had planned today. The second part of the work that I had planned today was that we would do some extra practice with the reference angles. So find a spot in your notebooks. We're going to do a little bit of sketching, and we're going to find some reference angles. I have to get another piece of paper. All right. So we're going to sketch just for practice and then find the reference angle. Okay. Sketch and find the reference angle. All right, let's see. Let's do a couple problems here. Let's start out with 3 of them, and then we'll see how long I've been working you. Let's do 110 degrees. Let's call that theta. Since that's in degrees, you're going to give your reference angle in degrees, please. And then let's do 7 pi over 4. Let's call that beta. Okay, so for 7 pi over 4, since that's in radians, you want to give your reference angle in radians. And then let's do negative 5 pi over 6. Let's call that one alpha. Since this is in radians, you're going to give your reference angle in radians. Okay, so take a moment, sketch all 3, and find your reference angles. Okay, for 110 degrees, that's this angle right here. It's a little bit past 90. Make sure you have your arc with your arrow here to show that that's theta. I'm going to put theta here. You don't have to label it theta, but you can. And the reference angle is this angle here. So that's theta prime. And that's going to be, if this is 110, to get to 180, it would be another 70. So your reference angle is 70 degrees. Okay? And theta prime is your notation for the reference angle. A common mistake here would be to put 20 degrees. But remember, you always have to go to the x-axis. Always, always, always to the x-axis, never to the y-axis for a reference angle. Okay, this one's beta. So for beta, we need to go past 3 pi over 2, but not all the way to 2 pi. All right. So we end up here. Oops, that should be a 4. So we end up here. This is 7 pi over 4. The reference angle is this. So if this is 7 pi over 4 right here, and we fell short of getting to 8 pi over 4, the angle that's in between, that's your reference angle. I'm going to call it beta prime because this guy was beta. And that angle is pi over 4. So if we get to 7 pi over 4 and we don't quite make it to 8 pi over 4, the difference between those is the reference angle, and that's pi over 4. Okay, here's my next one. I don't have quite enough space there, so I'm going to move down. So it was alpha equals negative 5 pi over 6. All right, so negative 5 pi over 6 is right about here. When you sketch, you want to go in the negative direction. You're not going to quite make it to negative pi. That would be negative 6 pi over 6. And you definitely go past negative pi over 2. If you're having a lot of trouble with the sketching, by the way, you either need to email me to get extra help or email me and ask for some extra practice problems, because the sketching is a skill that you definitely need to have down. So to sketch negative 5 pi over 6, we're going to go past negative 3 pi over 6, but not get all the way to negative 6 pi over 6. Now for your reference angle, what you want is the angle between the terminal side and the x-axis. So you want this right here, okay? And I'm going to call that alpha prime, because if our angle is alpha, the reference angle is alpha prime. So what we want is the size of that angle. So from negative 5 pi over 6, how much further to get to pi over 6? From negative 5 pi over 6, how much further to get to negative 6 pi over 6? Well, that's going to be pi over 6. Okay, so that's our reference angle. And remember, for a reference angle, it's always positive. So even though this angle is negative, the reference angle is positive. We just take the absolute value, or just take the magnitude, just take the size. So what I want is just the amount of that rotation. I don't care about direction when it comes to a reference angle. Just make the reference angle positive. All right, let's try a couple more. Let's do 4 and 5. All right, for number... Oh, that's a good one. Let's do this one. Let's do 7 pi over 12. Let's call that theta. And then let's have beta be negative 40 degrees. Okay, so since this one is in radians, give the reference angle in radians. And since this one's in degrees, give the reference angle in degrees. So go ahead and same direction, sketch both, and then find the reference angle. Okay, 7 pi over 12. You have to go past pi over 2, because pi over 2 is 6 pi over 12, just by a little bit. And then the reference angle is going to be the angle between here and the x-axis. Okay, and it always has to be acute. So you want to go from here to here. You don't want to go like this way, because that would be obtuse. So this is our theta prime. And to figure this out, we want to remember we got to 7 pi over 12. So that's 7 pi over 12. Pi would be 12 pi over 12. We didn't get that far. So from 7 pi over 12 to 12 pi over 12, how much further would you have to rotate? That's the value of your reference angle. So it's 5 pi over 12. And then the last one here is negative 40 degrees. So if we go to sketch that, we're going in the negative direction. I don't make it to negative 90. So this is negative 40. This would be 0. So what is the positive acute angle between the terminal side and the x-axis? So if we look, that's this angle here. So I just need to know the amount of that rotation. I don't want this one because that would be obtuse. And I don't want this one because we always go to the x-axis, never the y-axis. Always go to the x-axis for your reference angle. So the size of this angle is 40 degrees. Remember, reference angles are always positive. So even if the given angle is negative, even if you're rotating in the negative direction, when you find the reference angle, you just take the size, the magnitude, just make it positive. So the amount of rotation here is 40 degrees. All right, thanks for watching, and I'll see you guys in class tomorrow.